Okay, here's Mr. G, and we are going to go over some more of these Newton's laws problems. All right, so here we have a pulley, and there's a string or a cord going over the pulley. It's attached right here, and then it's attached to a series of masses. All right, so let's just say each of these masses, let's say they're all identical. And let's just say they all have a mass of, who knows, 1 kilogram, right? And we want to find the tension in each of these strings. So there's T1, T2 is the tension in the string connecting B and C, and there's T3. And you know what, let's just call this T0, why not? That's the tension in this string right here. And so they're not all the same string, okay? So there's like 1, 2, 3, 4 different strings connecting these masses. So find the tension in each string. Okay, and well, we're going to do this by, first of all, drawing a free body diagrams. And again, where you have multiple masses like this, the easy way to do this, instead of writing a bunch of equations and a bunch of unknowns, is to lump stuff together, right? So for the first one, we just lump all of these guys together into one big mass and pretend that this is equivalent to this situation. So 1, 2, 3, 4 masses, all that are 1 kilogram. So I could replace that with a 4 kilogram mass. All right, so now finding the tension in the string is straightforward. The acceleration of the system is 0. Nothing is going anywhere. So think about it. Newton's second law. Net force is ma. If they're not going anywhere, then A is 0. Or for that matter, if they were moving with constant velocity, A would still be 0, right? So if A is 0, that means the net force is 0. Okay, so then now, free body diagram of this guy. The forces acting on this, well, there's gravity acting on it. And that's the weight of this guy, and that's equal to mg. So in this case, that is equal to 4 kilograms. And the value of g we're going to use is 10 meters per second squared. 4 times 10 is 40. And a kilogram times a meter per second squared is equivalent to a Newton. So then the tension in this top string is going to be 40 newtons. All right. The total forces in the downward direction have to equal the total forces in the upward direction. So if T is 40 newtons, well, if mg is 40 newtons, then T has got to be 40 newtons, right? Or if you wanted to write this out, we can do that. Look, again, net force is ma. So let's just say that down is the positive direction, if you want to. Then that means I would write, actually, you know what, let's make upward the positive direction. So then I'm going to write T minus mg is equal to 0, which means T is equal to mg. All right. So 40 newtons is the tension in the very top string. Now, how do I find the tension in the T1 right here, okay? So let's redraw this. Or actually, let me just erase this stuff here. You can always rewind this if you want to. If anybody's out there reading this or looking at this thing. Oh, this one, hello. right, so now, come on, get out of here. Right, so now we're going to find T1. That's the tension in the string between A and B. Well, what I'm going to do to do this part is I'm going to lump these guys all together. All right? And it's with those guys. Remember, each of these masses is 1 kilogram. So now this picture turns into this. There's mass A. All right. And bloop, bloop, bloop. There are 3 of those guys. So now that's equivalent to 3 kilograms. Okay. And you want to find the tension in this string connecting A with those other masses. So let's make a free body diagram of this guy right here. All right. So if it's 3 kilograms, then the weight of this is mg, so that's 30 newtons. And then we're looking for this upward force here. Well, once again, if the net force on the system is 0, then the total upward force has to equal the total downward force. So yeah, T has got to be equal to 30 newtons. T1 is 30 newtons. All right. In other words, the string that is holding up the masses below it, that tension in that string has got to be equal to the total weight acting right below it. So for example, let's look at the tension here with the very last guy right here. So I'll draw a free body diagram of this last mass. There you go. And this is mass D. And so there's a section of string, and that tension is T3. And then there's the weight of this mass, which is mg. And this time it's just the actual mass of that last mass. We're not lumping anything for this last guy right here. So mg is equal to, well, if the masses are all 1 kilogram, so that mg is 10 newtons. And that means that T3 is 10 newtons. So there you go. Problem done. Let's look at another one here. How about this guy? Okay. So here we've got a pulley, and this pulley it's not floating in space. It's actually like attached to the ceiling or something here. And so there's a cord or a rope hanging over the pulley, and it's attached to a box on one end, and it's attached to a little weight on the other end. And the whole system is at rest. Nothing is accelerating, right? So the acceleration of the system is 0 meters per second squared. And we want to find 2 things. We want to find the tension in the rope. And we also want to find the normal force acting on the box. If you want to know more about the normal force and tension and example problems, you should read your physics book. This is chapter 4 in your physics book. All right, just saying. So the tension, right? So there are a couple of different ways we could do that, right? To find the tension in the rope. Well, I'm going to look at this guy right here to find that. Okay. We haven't assigned masses yet, so let's assign some masses. I don't know. Let's say that this box right here let's say that's 5 kilograms. And this guy up here, let's say it's 2 kilograms. And the tension in a rope is everywhere the same for these problems that we're doing now. They're light ropes. And so if I want to find the tension here, I'm going to draw a free body diagram of this mass, the weight that's hanging on the end of this rope here. So here's this guy. And so there's a rope acting, and that's a force upward. That's tension. And there's the weight of this mass. That's the force of gravity on it. That's mg. And if this mass is 2 kilograms, then its weight is 20 newtons. 2 kilograms times 10 meters per second squared. 2 times 10 is 20. And a kilogram times a meter per second squared is a newton. So then how large does this tension have to be? It's got to be 20 newtons. Because the acceleration of the system is 0. It's not going anywhere. So the net force on all these components is 0. So yeah, so this tension acting in this string right here is 20 newtons. Now, the second part of the problem is to figure out the normal force acting on the box. So I'm going to draw a free body diagram of the box, all right? All right, so here's the box, and it's 5 kilograms. And so we want to draw now the forces acting on the box. So there's this rope acting on the box. It's pulling up on the box. And the tension in that rope we just found, right? It was 20 newtons. Yep. So there's an upward force here of 20 newtons. And then also there's the weight of the box acting down. That's the force of gravity on the box. That's mg. So that is equal to 5 kilograms times 10 meters per second squared. So the downward force caused by gravity is 50 newtons. So there's 50 newtons down, there's 20 newtons up, and you'll notice those are not the same force, right? So with these two forces acting alone, the system's not in equilibrium. So there has to be an additional force acting on this box to keep the thing from accelerating. And that additional force is the normal force. The table, the surface it's on, exerts an upward force. The normal force. So that's what we're trying to find now. How much force does this table, our surface, exert on the box? N. Okay. Well, since the system is in equilibrium, since it's not accelerating, the total upward forces have to equal the total downward forces. Well, the total downward force is 50 newtons. So there's got to be 50 newtons acting up on this thing. Well, there's 20 newtons, so what does that make N? Yeah, it's got to be 30 newtons. We could write this out as an equation, of course, so let's do that. Newton's second law. Net force is equal to ma. And because in this situation nothing is accelerating, the net force is 0. And so now, for example, if I choose up to be the positive direction, the net force on the system is N plus 20 minus 50. N plus 20 minus 50. Equals 0. All right. And this is a complicated way of saying if there's 50 newtons downward and there's a 20 newton upward force, what other upward force must be there so that the total upward force is equal to 50 newtons? It's got to be 30 newtons. So, solving this thing for n here, if we want to get complicated about it. So you subtract 20 from both sides and add 50 to both sides. So I get n equals 50 minus 20 newtons. So n is 30 newtons. All right. Problem done. Let's do one more. How about this one? Okay. All right, so boxes. Yeah, these guys love boxes. So there's a 10 kilogram box sitting on top of a 20 kilogram box, right? So here we might want to ask, what is the normal force on the 20 kilogram box? And so the normal force is the force the table exerts upward on this 20 kilogram block. Well, I'm going to make a free body diagram of that 20 kilogram block. I'm going to draw all the forces acting on it and just represent those with some little arrows. So we've got, well, how about the weight of this 20 kilogram box? That's equal to mg. So it's 20 kilograms times 10 meters per second squared. So that downward force is 200 newtons. And if there was not a box sitting on top of it, that would be the total downward force in the problem. But yeah, there's a 10 kilogram block sitting on top of it. That is exerting a downward force on the 20 kilogram block equal to the weight of the 10 kilogram block. So that force, it's the weight of this 10 kilogram block. It's mg. It's 100 newtons. Okay. So the 20 kilogram guy is getting squished because there's a block on top of it pushing down, and there's also gravity pulling it downward. So the total downward force on this guy is, guess what? 100 plus 200, it's 300 newtons total. And what keeps this block from falling into the earth is the table. So the table is exerting an upward force here, N, the normal force. And looking at this picture, you can see what N has to be. It's got to equal the total downward force. So guess what? N is equal to 100 newtons plus 200 newtons, and that makes it 300 newtons. All right. Problem done. Okay, then we'll go ahead and upload these now for you.